Okay, I'm going to go on to mute us, and you can start your introductory, John.
Okay. Good evening, everyone. Tonight's speaker is a planetary astronomer who watches over all of us as we sleep. If I may, a modern feminine equivalent of Paul Revere. She is Dr. Melissa Brucker, Principal Investigator for SPACEWATCH at the University of Arizona. She was always fascinated by the distant Kuiper Belt planetoids, and now she also tracks potentially hazardous near-Earth objects. Please welcome Dr. Brucker.
Thank you. So today I will be talking about the research group that I lead. We're part of the Lunar and Planetary Lab, which is the planetary science department at the University of Arizona. So just to get started, here's some vocabulary. We are studying near-Earth objects, which include near-Earth asteroids and near-Earth comets. And these are the objects that orbit the sun with perihelion less than or equal to 1.2 astronomical units. And another vocabulary word is potentially hazardous asteroid, or PHA. This doesn't mean they're actually hazardous. It's potential. And they're called that because of their size. So PHAs are 140 meters in size or larger, and their orbits can get within 0.05 astronomical units of Earth's orbit. It doesn't necessarily mean that the asteroid will get within 0.05 AU of Earth itself. And the other vocabulary word is virtual impactors. There are some near-Earth asteroids where we've observed them and we know they're real and their general orbit, but we don't know their orbit to enough accuracy to rule out any possible impacts with Earth within 100 years. So they do. So the people who do the orbit fitting will do a simulation of thousands of different possible orbits within the uncertainty region and see if any one or more might hit Earth. These are very, very, very low probability that they would hit Earth, and it's not something that you need to worry about. But it's our job to reduce the uncertainty so that we can cross off all those possible impacts. Okay, so I work for SPACEWATCH. It was founded in 1980 by Tom Garrels and Bob McMillan. And it started as a discovery survey using a 0.9 meter telescope on Kitt Peak. And SPACEWATCH basically pioneered using CCDs for solar system astronomy. So we were the first to measure an asteroid with a CCD, the first to discover an asteroid with a CCD, and discover a comet. And then also, in addition to all of those firsts in the late 1980s and early 90s, we also discovered the second known centaur, Pholis. Centaurs are medium-sized icy objects that orbit in between the giant planets in the outer solar system. We also discovered Runa, which is a Kuiper Belt object, so in the belt of objects around where Pluto is. And if you are familiar with the DART mission, NASA's DART mission, we discovered Didymos, the primary of the moon Dimorphos, which got hit by the DART spacecraft. And in the corner, you have a GIF of the discovery images from when our observer discovered it in 1996. Okay, where do we observe? We observe on Kitt Peak. This is the same mountain that has the NSF's Kitt Peak National Observatory. So most of the other telescopes you see in the background of this picture are telescopes belonging to Kitt Peak National Observatory. And the area in the foreground is operated by Steward Observatory, which is the astronomy arm of the University of Arizona. Steward Observatory provides access through a telescope allocation committee to all scientists, all astronomers that are in any of the 3 state universities. And if you are not, but you have a collaborator who is, you can get access that way by proposing for time that way. So the telescope in the foreground is the Steward Observatory Bach 2.3 meter or 90 inch. And it is scheduled through the Telescope Allocation Committee. And we use that almost half of the time now for 2 separate projects. The next telescope behind that is the Steward Observatory 0.9 meter. We have had exclusive access to that telescope since 1982. It is actually the original telescope that was on campus in 1922. And so the tube of the telescope is original. We have new optics and new mirror and new cameras. The other telescope is a Lunar Planetary Lab telescope that was built for SPACEWATCH in 1997, and we started using it in 2002. So we are also the sole users of that telescope as well. These are all optical telescopes, and we mainly do imaging with them. Okay, this is what the historic telescope looks like. You can see on the right-hand picture, there is a cylinder sticking out of the front end of the telescope, and that is the dewar filled with liquid nitrogen that keeps our camera cold. So our camera is further in behind that dewar. That is the outside piece. And that camera was designed and built by SPACEWATCH staff in 2002. Okay, this is what the 1.8 meter 72 inch looks like. It is actually all black. The flash made it look light gray. This is, so unlike the 0.9 meter or 36 inch, which is equatorial mount, this one is alt azimuth, so altitude and azimuth. So everything above the brace, everything you can see in the right-hand picture rotates around a circular rail, kind of like a train, like train tracks. And then it will tip in the direction, I believe, away from us in this point of view in the picture. So this is a setup that couldn't really be used before there was a lot more computing power. With the equatorial mount, it just follows the rotation of the Earth. But with the alt azimuth, you can point in any direction, so you have more computations that your software needs to do to point it in the right place. Okay, so SPACEWATCH's main goal, we started as a discovery survey for asteroids and other objects in the solar system, and we have transitioned to do follow-up. So we look at objects that are just discovered, or near-Earth objects that were just discovered, or ones that have been discovered for a while, but they need more observations so that we can lower the uncertainty in our knowledge of its orbit. But the things that you probably see the most where you live are fireballs and meteors. And so this is a plot of the fireballs that have been reported to the Jet Propulsion Lab from government sensors. And if you are interested, the big red one over Russia is the Chelyabinsk impact. So these are all very small things. The largest one on there was Chelyabinsk. It was about 18 meters across. Okay, but occasionally people who are discovering asteroids discover one on its way in to hit the Earth. And these are all of the asteroids that were discovered on their way in. These were not dangerous asteroids. They were all 1 to 2 meters in size. And so when they hit the atmosphere, they burned up. A few of them did result in meteorites on the ground. And the first one, 2008 TC3, was fantastic. Some expeditions went out to collect meteorites in there. So in that area, and quite a few were collected. And it's called the Almacid. I'm not going to pronounce it properly. It's I think no, I'm not going to pronounce it properly. Sorry. It was in my presenter notes. You may notice that 4 of them were discovered by the Catalina Sky Survey. The Catalina Sky Survey is a survey in the Tucson area. We actually work from the same department at the university. And they are one of 2 major discovery surveys that are one of the 2 major discovery surveys finding new discoveries. So you can see here there are a wide range of locations where the meteorites landed. And this is a photo of one of the meteorites from 2023 CX1 that landed in northern France. And it was visible from Great Britain and northern France on its way in. So not all of the things that hit the Earth are 1 to 2 meters. Here's a photo of Meteor Crater. This is in northern Arizona, and it's gigantic. This was a very large metallic asteroid. So when it hit the Earth with an impact force of somewhere between 20 to 40 megatons of TNT. It would have wiped out about 50% of all the life within over 800 miles. Okay, you also may have heard of the Tunguska event in 1908. This was in what is now Russia, and it flattened the forest in a very, very large area. But the impact was not as damaging as Meteor Crater because this asteroid was a stony asteroid. So composition matters. Size matters and composition matters. But people were aware of the Tunguska event, but they didn't really think that asteroids were hitting in the early 90s. They didn't think that asteroids would still hit the Earth. They thought that, well, I'm sure some people did, but it was thought that we didn't really have to worry too much about it until the discovery of comet Shoemaker-Levy 9 in 1993. This comet interacted frequently with Jupiter, and when it was discovered in 1993, it had already been pulled apart into many pieces. And side note, the discoverers, the SPACEWATch, after it was discovered, measured it and confirmed that it was real and scary for Jupiter. So it impacted Jupiter in 1994, and these are images from Hubble Space Telescope in different wavelength bands. And each of the size of those impact storms are larger than Earth. And so now people were like, oh my gosh, this is a huge impact. We should maybe look into what's going on with the asteroids in our area. And so in 1995, the Space Guard survey began with a mandate to find 90% of near-Earth asteroids that are 1 kilometer in size and larger. So as a result of that, NASA created a near-Earth object observations research program. And so the community, the near-Earth asteroid community, discovered a lot of these 1 kilometer and larger asteroids, and they found almost what they thought was almost all of them. And in 2004, the asteroid Apophis was discovered. And it was discovered by Tucker, Tholen, and Bernardi at Kitt Peak, which is the same mountain that I observe on. And when they discovered it, they called over to the SPACEWATCH telescope and asked, "Hey, can you check and see if you see this asteroid too?" And we did. So, and then later we were able to look up in our data archive and find images that contained Apophis before it was known, before it was discovered. Part of the sentence got deleted. So the initial orbit calculations for Apophis, which is relatively large at 340 meters, said that it might hit the Earth in 2036. So that was a really big deal. And so lots of people started observing it whenever it would pass by Earth close enough to see it. And in 2013, the Goldstone Solar System radar, which is part of the Deep Space Network that communicates with all of the spacefaring spacecraft, they were able to observe Apophis, and their measurements, because they can do radar ranging, ruled out the 2036 impact. So we don't need to worry about Apophis, but it was very worrying for a couple years. Okay, so Apophis was discovered, everyone is concerned, and so Congress mandated in the George E. Brown Act that was passed in 2005 that NASA must find and catalog at least 90% of all near-Earth asteroids that are 140 meters and larger by 2020. And that's awesome. We've been working on it. They didn't give us any money. So by 2010, we kind of figured, I wasn't in the field at the time, but we kind of figured that we wouldn't be able to finish by 2020. We've been working at it diligently and adding to the inventory, but we didn't make it. So here's this. So that was in 2005. In 2013, we had the Chelyabinsk event over Russia, and here are some images of that Chelyabinsk event. This object was only about 18 meters in size, but it was very well documented, and it also came from the sun side, so it was a surprise. And it was known that a known near-Earth asteroid was going to have a close approach to Earth that day. And so some people thought that it might be that asteroid, but that asteroid was going in a different direction than Chelyabinsk was. Also, I learned later that there is a nuclear station in that area as well. So we're very happy that the people in that community were already aware of near-Earth asteroids. Okay, so this happened, and there's a lot of footage. I have some links later if you are interested in them. It exploded about 14 miles above the ground with a force of about 300 to 440 tons of TNT, and it blew out windows over a very large area. No one was hurt directly by the asteroid or its fragments, but it was so bright, it was like a second sun in the sky. And so a lot of people who were indoors went to the windows to look out. But as we know, light travels faster than sound, and shock waves from explosions travel at the speed of sound. So they were looking at the brightness, and then the shock wave arrived, and the windows and even some garage doors and walls fell down. And that's how most of the people that were injured. But again, this was relatively small. Our mandate is to find 140 meters and larger, and that is based on a damage estimate. This one is well below that, but it can still create a lot of local damage. Okay, so after Chelyabinsk, NASA already had the Near Earth Object Observations Program, and they created then also a Planetary Defense Coordination Office with a Planetary Defense Officer. And this is part of NASA. It was officially established in 2016, but the same people who are running the Near Earth Object Observation Program are the same people who became the Planetary Defense Coordination Office. We are funded fully through the Planetary Defense Coordination Office through grants. Well, actually one grant, and that is the Yearly Opportunities for Research in Planetary Defense. This office also has run the DART mission to impact Dimorphos. It oversees the NEOWISE infrared spacecraft and the future NEO Surveyor, which is also which will be a Discovery infrared space telescope. And they also work with other agencies, international and federal and local, for example, to practice emergency scenarios. So they create an exercise where they create a fictitious asteroid and that's coming to hit the Earth, and they model with this practice exercise, what is the asteroid like? What can we tell about it? Where might it hit the Earth? What kind of damage would be created if it hit in different places on the Earth and things like that. But it's completely a fictitious exercise. Okay, so planetary defense can be split up into 5 different categories: finding things, tracking things, characterizing them, mitigating the danger, and then assessing the state of the community. So discovery surveys is what needs to happen first, and Catalina Sky Survey and which is part of University of Arizona, and PanSTARRS, which is affiliated with the University of Hawaii, together discover most of the new discoveries that happen for near-Earth asteroids. There are several other discovery surveys as well. And then there are a lot of groups who track the asteroids once they're discovered, and that is what SPACEWATCH does. And the discovery surveys do also incidentally can measure the other asteroids after they're discovered as well. So our goal here is to know more accurately, very accurately, the orbits of the asteroids by measuring where they are in the sky and measuring the particular time at which we measured them. You also can do characterization to learn more about them. So with invisible infrared or radar wavelengths, you can take spectra of the asteroids if they're bright enough to collect enough light for spectra, and that is usually done in near infrared and visible. If you are looking at it in infrared with an imager in at least two different wavelengths, you can estimate its size by comparing the amount of light reflected from it in visible to the amount of light emitted in near infrared. If you take a series of lots of images in a row, hopefully over several nights, you can measure the brightness of the invisible light of the asteroid in each image and string that together into a curve, and that light curve will tell you about the shape and the spin rate of the asteroid. And if you are using radar, you can, depending on how radar bright it is, you can precisely measure how fast it is moving towards or away from the Earth. And if you can get radar imaging, and the object is bright enough, you can get an idea of its shape and its rotation. Okay, so after characterizing, you can mitigate. If this is an object that is actually really scary, you want to be able to do something about it so that it doesn't hit Earth. And so for that, NASA and other agencies practice. They make up exercises, which a lot of us participate in, where we are making an observation of an asteroid that's not actually hazardous, but pretending it is. And even the people who model impacts participate in these exercises so they can inform the agencies on what the next step would be to help safeguard the people in the area where this fictitious asteroid might fictitiously hit the Earth. And then this is a circular loop. So all along these steps, there's assessment on how well are we doing. So how well are we doing? So this is a graphic. I added the red diagram on the top. But this is a graphic that the Planetary Defense Coordination Office uses a lot. And so how are we doing in the assessment? This is a chart that I downloaded today. We know of 35,440 near-Earth asteroids. There are a lot more, but this is how many we know. We know of almost 11,000 that are 140 meters and larger, and about 860 that are 1 kilometer and larger. We know basically where all of the 1 kilometer and larger near-Earth asteroids are based on models of the population. For the ones that are 140 meters and larger, not so good. This was the size category that we were supposed to find 90% of them by 2020. We're at 44% as of last year. No, 2 years ago. But it's predicted that the NEO Surveyor Telescope and the Rubin LSST survey should, throughout their lifetime, and especially in the first couple of years of each mission, discover most of the remaining asteroids in the course of their surveys. Okay, so here's another assessment of how we're doing. This chart is based on data in the Harris and Chodas paper from 2021, and a new population model was published this summer, actually last month, where people have taken the information about all the recent measurements and used that to model what is the part of how much of the population haven't we seen yet, how much is left out there. You can see on the right-hand side, the percentage of very large asteroids that we know went down. And that's not because we lost any, it's because the population model changed and the total number that is expected went up. But we still know basically where all of the large things are. And the people who work on this are JPL, the Jet Propulsion Lab Center for Near-Earth Object Studies, the European Space Agency's Near-Earth Object Coordination Center, and the Near-Earth Object Dynamics site, which is run by SpaceDis in Italy, but they do it in conjunction with the European Space Agency. Okay, so where do we fit in? We're in the search, detect, and track part. And so what do? We use the 1.8 meter and the 0.9 meter 24 nights a month. And this is the dark and gray time. We don't use these telescopes during the full moon, about 5 to 6 nights centered around the full moon. And we do this to measure astrometry of asteroids. So what we're doing is measuring the precise positions of the asteroids and also recording the precise time when we measured them. And we take those measurements and submit them to the Minor Planet Center, which is the international clearinghouse for all measurements of astrometry of all objects in the solar system. So we use that for 24 nights. We also use we have a small Finger Lakes instrument camera that we use at Cassegrain on the Bach telescope, which goes through the telescope allocation committee. We usually get 6 nights of full moon time to use that. And we also are part of a joint discovery survey with the Catalina Sky Survey and the University of Minnesota. And for that, we also use the Bach 2.3 meter and their wide field imaging camera about 7 nights each month during dark and gray time, so when the moon is not up. And this survey began in the fall of 2019, and it's already in the top 10 of telescopes for discovery from 1993 to present, even though it just started in 2019. And the reason that occurred is because it's one of the very largest mirrors that is used for discovery of solar system objects. Most of the discovery telescopes are on the order of, are about 1.5 meters in size. Okay, so when we're doing the astrometry, we need to prioritize which near-Earth asteroids we're going to look at, because there are a lot of them. So our highest priority are the virtual impactors, the things that could hit Earth within the next 100 years, although that's very, very low probability. And we look up information about them on the JPL website called Sentry and Neodice, their impactor webpage. So all of the information that we use to do our jobs regarding our targets is found online. So we're not hiding anything. You have the same access to this information as I do. The only difference is I sometimes get a lot of email. But all of the information in the email is also available online. Okay, we also look at potential discoveries. So when a discovery survey discovers something, they submit 3 to 4 measurements that all occurred around the same time, sequentially. But that's not enough measurements to get a good orbit. And so we look at these objects that are posted on the Near-Earth Object Confirmation page and Scout. So Near-Earth the NEOCP is a Minor Planet Center page, and Scout is a JPL page. And that has information on these objects that may or may not be real, or they may be asteroids, or they might be artificial satellites. And so collecting more observations on these helps determine if they are near-Earth asteroids and helps secure their orbits. We also look at candidates for detecting the Yarkovsky effect. The Yarkovsky effect is the effect of non-isotropic radiation on an asteroid. So if the sunlight is shining on one side and the asteroid rotates just like the Earth rotates, when that heat radiates off after the sunshine has hit it, and then some of that energy will radiate off as infrared light, but the asteroid is rotating. So this difference between the direction of the incoming sunlight and the outgoing radiation acts like a tiny thruster. And so it moves the asteroids in their orbit just a little bit, but over time that can add up. So this is an effect that we want to study so that we can see how it affects the asteroids over time, especially for the near-Earth asteroids, where it can change their orbit into something that's not quite as safe. But also, again, not anything you need to worry about. We observe potentially hazardous asteroids, but the ones that will actually get close to Earth in the next 60 years, and not just the ones that have orbits in this general area. And we observe asteroids that are listed on one of the priority lists online, and asteroids that are going to be targets of planetary radar. If the position isn't known precisely enough, the radar beam, when they broadcast the radio waves to bounce off the asteroids, they need to know more precisely than we would with an optical telescope where the object is. So we want to lower the uncertainty before they point their radio telescopes at it. We also look at asteroids that have been observed by the Space Telescope NEOWISE. May it rest in peace. It shut down last month, I think, because it was getting too close to the Earth's atmosphere. And we observe these because, it's an infrared space telescope. It's expensive to get that data. So once we know the characterization, we know about its size and its reflectivity from the spacecraft, we don't want to lose the asteroid and not know where it is anymore. We also look at targets that are asteroids that are potential targets for spacecraft and smaller asteroids that will get close to Earth compared to the potentially hazardous asteroids that will get close to Earth. Okay, so this is what our images look like. For the 0.9 meter or 36 inch, it's a mosaic camera. And so you can see 4 different CCDs, and each CCD has 2 amplifiers on it. And that's why the shading, the background shading is slightly different. So can you see the asteroid in the GIF? This one is pretty straightforward. I've centered it in the image here. This was a bright asteroid, and it turned out to be right where it was predicted to be. So it was pretty easy to find. And here it is outlined. With the 1.8 meter, 72 inch, I chose an example that's not so easy to see. And so what I did to make it clearer for myself is I changed the contrast and I flipped black and white. So now instead of having white stars, we have black stars. The reason the stars are trailed is not because we were tracking non-sidereal. We were not tracking at the rate of the asteroid, but we knew that the asteroid was not bright enough to see in a single image. So we took a series of images and then stacked them along where the expected position of the asteroid would be in each image. So the asteroid, the light that was collected from where the asteroid was, we collect it all in one spot. And that means that when we shift the images, the stars, each individual image of the stars gets spread out into a line. So I had to adjust the contrast and zoom in a lot to find this one. Okay, so that was the tracking. That is our main function for NASA. But we can't tell more than just where it is and its approximate size and brightness from measuring the astrometry or the location of where it is in the sky at a particular time. So other people do characterization, and one form of characterization that you can do is create the light curves, which I mentioned earlier. So this is a light curve that we collected the images for with the Bach 2.3 meter. And I chose this example because it's animated. So you take a series of images, and in each image, you measure the brightness of the asteroid compared to the brightness of solar colored stars in the image. And then you run it through a program that helps you determine what the period of the rotation is. So, so for asteroids, they're usually not spherical. For this purpose, we hope they're not spherical. But as they rotate, there's going to be a longer side and a shorter side. So to make one complete rotation, you're going to see a long side, a short side, a long side, a short side. And so they should have 2 peaks in the rotation. And when you fold all the data together, you can determine what that rotation period is once you get all of the different passes lined up. Okay, if you're not taking spectroscopy, or you're not measuring the colors of the asteroids, and you're not doing light curves, and you have a space agency, you can actually learn about and characterize the asteroids by sending a spacecraft there. So on the left are images from the Hayabusa 2 spacecraft from JAXA, and they visited Ryugu and brought back a sample to Earth. And on the right is the NASA spacecraft OSIRIS-REx, which visited Bennu. and brought samples back to Earth. The OSIRIS-REx mission was actually operated out of the same department that I work in. And we do have some small samples in the basement of our building that the scientists are analyzing with all of their machines. Okay. So there have been several international campaigns, and these are a few of the ones that we participated in. So these are all practice. There was nothing scary about any of these asteroids. For 2012 TC4, this was a very small asteroid, and it was going to have a close approach to Earth. But it never had any possibility of impacting Earth. So we did a practice exercise of trying to recover it as if it would be hitting Earth, but it was a practice, and to see how quickly we could find it, since its uncertainty of its location was pretty high. And this actually led to the faintest ever at the time measurement of an asteroid, and it was by the Very Large Telescope in Chile, and they measured it when it was a magnitude of, I think, 26 to 27. But at the time, it was the very faintest measurement of an asteroid with a ground-based telescope. And so we did successfully recover it, which was awesome. The next year, we observed 1999 KW4, which is a binary asteroid. And so a lot of the work that we did and other groups did for this was to collect light curve data, series of precise photometry measurements of the binary system over time. We also did the same for Apophis. It had a close approach in 2021 and 2022. And so we observed that along with many other people. There were so many observations of that asteroid in many different characterization methods that it now has no known possible impacts at all within the next 100 years. Remember, the community had already ruled out the scary one from 20 that would have happened in 2036. Okay, we also participated in the DART mission. And so for the DART mission, NASA's DART spacecraft was going to hit the moon of an asteroid. The asteroid was called Didymos, and its moon was called Dimorphos. And the goal was to hit the moon with the spacecraft and see how much the orbit of the moon changed going as it goes around Didymos. And so the goal was to shift the period of the orbit by, I think, at least, I think it was 7 minutes, a smaller amount than what happened. What happened was they managed to shift the period of the orbit by 32 minutes. So that was awesome. NASA proved that they can actually move an asteroid. Why did they hit a moon instead of an asteroid instead of a solo asteroid? It's a much faster experiment. If you hit a solo asteroid, you have to wait as it goes around the sun a couple times, or quite a few times, before you can measure the difference in the orbital period of the asteroid around the sun. But if you hit a moon, its orbital period around the primary asteroid is short, and so you can see the change faster as it goes around and around. Okay, so that was Mitigate, hitting it with the asteroid, hitting Dimorphos with the asteroid. And for the population of near-Earth asteroids, the smaller you are, the more numerous you are, and the less impact it would have if it hit Earth. There are so many small, little tiny asteroids that the percentage of the ones that we know of is very small, just because there are so many total. And So the very large asteroids, there are very few of them. And because there are very few of them, we basically know where all of them is. Well, all of them are. But because they're very big, they can create a lot of damage. So the DART team created this animation illustrating the differences in the different size ranges. I love that there's a dinosaur in the largest one. Okay, for the DART mission, they involved telescopes all over the world. And if you look in the upper left corner under Arizona, it says SPACEWATCH 0.9 meter. So we spent a lot of time taking images for light curves of the Didymos system, October through partway through January. And here are our discovery images again. And this is one of the animations from the DART spacecraft as it's approaching Dimorphos. And is there. So it looks like lots of small pieces and dust, kind of like cinders, the shape, like these sharp edges. The naming theme for the features that were identified are musical instruments. Unfortunately, most of these probably no longer exist because that is where the spacecraft hit. So the white rectangles represent, the square represents the bus or the main part of the spacecraft, and the longer rectangles are the solar panels. And here are some images from the Italian Space Agency Licia Cube. It was a CubeSat. And here is our ground-based images from South Africa. So this really was a worldwide campaign to take data of it. Here's an image of the trail of material that was blown off of the moon 2 days after the impact. And here are images from Hubble and the James Webb Space Telescope as well. The star-like pattern that you see is mainly from how the mirrors are aligned inside the camera, inside the spacecraft. But there is a lot of material that is, it's not all artifact. A lot of it is just the material that was blown off. In fact, there was a study done that counted like at least 9 boulders in the Hubble images. So here's the image that we took. So that the impact was in the fall. 109 days later, we were still able to see the tail. So the tail starts on the left-hand side of the thin line in the center and goes towards the right. This was 109 days after the impact, and we're only using a 0.9 meter telescope to measure this. So it's pretty crazy. And here are 2 of the light curves created from the images that we took in late November and early December. I don't have an image of it here, but one of the DART team scientists had a program to measure Dimorphos with the Hubble Space Telescope, and he was still able to see the tail in July when the impact was in late October. So that is just fantastic. They've learned a lot about this. They measured based on the amount of change in the orbital period of Dimorphos. They measured how much momentum was added to the moon, and it was enough that it added them. So if there were nothing blown off, the momentum enhancement would just be 1, like it wouldn't change. But there was so much material that blew off, that was thrown off, that it increased the momentum by 3 points, by a factor of 3.6. So it's very interesting and something that would be really cool to study, how you will do the best way to move an asteroid out of Earth's path. So what is coming up? Apophis. In 2029, Apophis, the 340-meter near-Earth asteroid, will so closely approach Earth that people will probably need binoculars, but people on the other side where it will have its closest approach won't. It will be about magnitude 6 at its very closest. It will be moving very, very fast, though, from our point of view. It will be about as close as the geosynchronous artificial satellites. It's such a big deal that the OSIRIS-REx spacecraft was able to get an extension and is now called OSIRIS-APEX because it is going to investigate Apophis right after closest approach. Okay, I think that's most of my main slides. So we are funded by NASA's Planetary Defense Coordination Office. And we also have funding from the Brinson Foundation of Chicago to do light curve work with the 0.9 meter. Our telescopes are on the mountain Yolicon Dog, which is in the Tawna Reservation inside their nation. And we are very happy to be supported by all of the other people listed below here. Thank you. Okay, see, there's a message in the chat.
Yes.
Are there plans to put an observatory in space? So the NEO surveyor won't be able to cover the whole blind spot, but it will be able to search for asteroids, I think up to 40 degrees down to 40 degrees elongation. So they will be able to survey an area that we cannot see from Earth. And this one, unlike NEOWISE, which was an extended mission of the WISE infrared spacecraft, the WISE Infrared Survey Explorer, NEOWISE was not designed specifically to discover near-Earth asteroids and characterize them, but the NEO surveyor will be designed specifically to discover near-Earth asteroids.
I have a question. Several. I guess the approach speed, is that determined by radar? Is that how what do you measure?
So we're not measuring the speed, we're only measuring the right ascension and declination and the time at which when we make the measurement.
I guess when I saw that little pinprick of a light through, I wonder how much can you get from that? How do you know plans and such?
So when we look at it, there is an orbital solution already. So we put our software inputs the current ephemeris or the path of the asteroid as seen from our location on Earth into our software and tells our telescope to point there. And so occasionally we look at asteroids that are bright enough to only need to take one image to measure its brightness and its location. But often they are not that bright. And in fact, we don't want to focus on those very bright things because other people can. Because we have larger telescopes, we want to focus on objects that only people with similar size telescopes can look at because of the faintness of the objects. So we start with the orbit as well as it is known, and we use that as our input. And when we stack the images together, we use the rate of that initial orbit calculation, how fast it's supposed to be moving across our screen. And that's what we stacked the images along. If it looks weird, if it's not circular, then we can restack it with the speed measurement that came out from our first measurement. And so we can restack it with the adjusted rates and hopefully get it from being elongated to being circular in our images. But we're not actually measuring its motion. We're just comparing where it is to where the stars are in the star catalog.
Okay, it's still, I guess I'm still confused because that's two-dimensional and
Yes,
I'm
it is.
trying to, right, and so you're looking at it against the star field.
Yeah.
So how do you know if it's coming or going? How-
We can
and-
look at the ephemeris.
I mean,
We don't have to calculate whether it's coming or going.
oh,
That's our job. Our job is just to measure its right ascension and declination and time, and then the Minor Planet Center has to do all of the math.
I see. Oh, okay.
And
Now
it's very nice for our end.
the light cycle, that we're seeing, the sine wave sort of thing,
Yes.
just indicates that it's rotating, right?
Yes. So you would see more. So I'll do a pen and smaller. So when the asteroid was facing this way towards you, you would see more light, total light. And then when it rotates, you see less and less light. And then the minimum amount of light when it's like this. And then as it keeps rotating, you'll see more and more light. And then you'll get the minimum amount again until it's back facing the same way.
And how often are you able, with so many out there, how often are you able to go back and check your accuracy in orbit?
The Minor Planet Center puts out reports.
Oh, okay.
But when we gather information at the beginning of each night, it has a measurement of what they think the uncertainty is of the position in the sky.
I see.
So we would choose targets that have higher positions in that report. And so we want to choose ones with high position so we can higher uncertainty so we can lower that uncertainty after we make our measure because of making our measurements.
And how often is a planetoid lost? Where it just goes up?
There have been a few that should not have been lost, and we're not sure why they haven't been recovered yet. There's one from 1979 that really should have been recovered by now, just by chance. The people who do follow up and the surveys, because they go back to the same regions of sky over and over again, do end up picking up the objects that have been discovered in the last couple months. It's pretty easy it depends on how fast they're receding from Earth, right? The farther away they are, the less light that gets to us. So we take our targeting software filters out all the things that are impossible to see from our telescopes, based on how bright they're predicted to be, or whether they're just like below the horizon, or there would be only up during the day. So our software does a lot of filtering for us ahead of time. And then we can just choose from the list of objects, and we put a tag on it in the table, in the targeting table, of if they were one of those particular ones we really like a virtual impactor or a PHA. So each of them has a label on it, if they fit into one of those categories. And so we would choose one with the label that had a high uncertainty or hasn't been seen in quite a few years.
And occasionally I'll see a note. Now, when the media grabs this, you must wince quite a bit, but occasionally it says this was never detected, and there's a small asteroid going between the Earth and the Moon. Do you have meetings where everyone sits around and said, how did we miss this one? Or
No, almost every asteroid I've seen in the popular media is one that I don't care about. And generally, they're just too small for us to think is important. My favorite analogy, though, is the giraffe-sized near-Earth asteroid. That was my favorite description that they gave one. Because I really think that they are purposely trying to come up with cute analogies for size because Americans don't like using the metric system. But So I probably wouldn't be interested in anything that was less than 50 meters across.
Wow, okay. Thanks.
See lots of hands raised.
Yeah.
Mic open?
Yes.
I use our 26-inch cast grain for astrometry of PNOs submitting to the MPC. I suspect that the SPACEWATCH data processing pipeline is much better than mine and could produce better astrometry on fainter objects. Is it in the public domain or is it proprietary?
It is not in the public domain, mainly because it's so tailored to our system. You saw the image of the mosaic image. Our software has built up over time, so that camera went into practice in 2003. So it's had 20 years of changes made to it over time. So it's not that we can't make it open source, it's just probably not documented well enough to share it, and it's very tailored.
And I probably wouldn't want to copy code anyway, but are there any special techniques that have been documented? You know, if not the code, is there a higher level view?
So there some of the surveys are working on making their code public. NASA started, I think, couple years, 2 or 3 years ago, they instituted an open science and data management policy, where any newly starting grants that have code that create science measurements, they need to have their code open source when they publish it. Now, our science is the astrometry, and what we do to measure the astrometry itself is pretty standard. We don't have any like weird things and just here's an image, there's the dot, right? And so we are not publishing our code right now. Maybe if we had new software, we might, we don't have any new software really.
Yeah.
You could check out the Catalina Sky Survey, I think, has already started posting their code, and you could check for Astronomical Research Institute, which is another follow-up group. That they have telescopes in Indiana, and they also use some telescopes in Chile at Sierra Tololo.
Okay. Well, not looking for code, but you said it's pretty standard. Is there like a standard reference that's considered the best practice?
So a lot of the amateurs use the Astrometrica, and we actually do use Astrometrica as a fail-safe for the 1.8 meter if our software is not happy with the images.
Okay, thank you. That helped.
Yeah.
When DART hit the moon and that material was blown off, is some of it falling back, being pulled by gravity? And if so, are there models that what effect that will have on the orbit?
Probably, yes, some fell back. What they were able to measure is the momentum change due to the change in the orbit. There was so much material just surrounding the system itself right after impact that it was hard to see the details. And the DART spacecraft didn't exist anymore. So there was the only other in situ observer were the Licia Cube, Italian CubeSat spacecraft. And so there are a lot of images that those spacecraft took as it was circling around, but it wasn't super close to the moon for safety. But there are journal articles that have been published about describing like the amount of material that the net amount of material that was expelled based on the change in the momentum.
You said earlier that the impact of the dart caused the ejector to come off it, and those boulders, the lessening of those boulders increased the momentum of the moon. Did the impact of the dart itself not increase the speed of the moon?
Yes, but what the only thing they can measure is the net change in the momentum. So they have, I'm sure that they have modeled what portion was the spacecraft, because they know how fast it was going and they know how much it weighs, how much the mass was of it. So the end result is the sum of the momentum of the spacecraft hitting Dimorphos and the momentum of the material that came off.
Thank you.
So with the Apophis 2029, you said you guys going to go through geosynchronous orbit, if I'm remembering correctly?
Yes, it's
Is-
going to fly through it. It's not
Sure.
going to, yeah.
So is there any concern of like losing like GPS or any other spacecraft that are in geosynchronous orbit, either from collision or just gravity pulling it? There's no concern? Oh. And my other question would be, you said the telescope has liquid nitrogen, if I remember right?
Yes.
Is it cooled for the same reason that the James Webb is?
Yes, so the electronics of the camera, when they're warmer, the electrons in the camera,
Like
Can-
they shut around and.
yeah, the warmer it is, the more noise, background noise is in your data. So we chill the back of where the CCD compartment is down to negative 140 degrees
What is
so
that?
that- Celsius.
130,
130 Kelvin?
130.
Okay.
Next question.
About the impact and the momentum change of the moon. Have you observed any changes in the angular momentum of the moon?
Oh, I have not read the paper about how the light curve has changed, but they were Petr Pravec, who is based in the Czech Republic, and his team were organizing. He's an excellent photometrist, and he helped organize the different groups who were taking measurements later on after the impact. I just haven't I'm followed up on that paper yet, but they did find that the rotation was actually changing over time quite a ways after the impact. So the combined light curve of Didymos and Dimorphos was not constant for I think they were still noticing it like 3 months later, that it was still kind of shifting a little bit over time, as Dimorphos is relatively close to Didymos, and so it gets tugged gravitationally on different sides, and so it is trying to re-equilibrate after it got moved.
Any other questions? Any questions from anybody online? All right, John, I think we're good.
Thank you, Melissa. Thank you.
You're
very
welcome.
much. This is a subject near and dear to all of us.
Well, if people come up with questions later, feel free to email them to me. To
Very
forward them.
good. We'll do that. Thanks for taking the time to speak with
You're
us.
welcome. Thank you for inviting me.
Great. Bye now.
Bye.